Next, let's get into the language a little bit more and talk about some of the constructs that we use for modeling in VHDL. In this section, we'll look at constructs like the constant, what the signal is, various operators that we could use, how to make signal assignments, types of processes, sequential statements and where they're used, what variables are and how they compare to signals, and then finally user-defined types. Constants are used to assign a value to a name. They are used to make your code more readable and add flexibility to your design. By using constants, I can change things like bus widths or even enable/disable design features just by changing the value. Generics are essentially constants whose values can be passed in from other modules and changed at compile time. Local constants, invisible outside of the model, are declared in the architecture declaration section. To declare a constant, you use the keyword constant followed by an identifier name, the data type, :equals, and the value you are assigning to that constant. The value must be valid for the constant's data type. So in this example, you can see that the identifier bus width is being assigned, is being set up as an integer and being assigned a value of 16. Constants cannot be changed during design execution. Signals represent the physical interconnects or wires that allow processes to communicate. Signals can be declared in the package, they can be declared in entities or in architectures, though most often they're declared in the entity in the architecture. Signals that are declared in entities are essentially your I/O. Signals that are declared in the architecture are internal signals that you use to connect blocks together, invisible to the outside world. So looking at this example here, we have I/O signals that are being used to communicate with the outside world. We have the process on the left, which is a MUX. It generates an output that it drives to a signal that then is read by the process on the right, which is a register. The output of the register then feeds a signal that is used to drive outside of the model. To declare a signal, you use the keyword signal followed by the name of the signal, :, and then the data type for that signal. So in this example here, you can see that I'm creating a signal called temp. Its data type is standard logic vector, 8 bits wide. The signal assignment operator is a less than equal to sign. So if I want to assign a value to temp, I can say temp gets the value of and then the value. If I'm assigning a bus value, then I need to surround that bus value by double quotes. The 93 standard of VHDL also supports using hexadecimal notation. So in the second example, you can see I'm assigning temp to the value of AA in hex. If I want to pick off a single bit of the bus temp and assign it a value, then I can use parentheses to select the array bit. For single bit, I can use a single quotes instead of double quotes. So here I'm assigning a 1 to bit 7 of temp. You can also do bit slicing using parentheses as well. So here I want to assign the value 1010, the bus value, to bit 7 down to 4 of temp. As I mentioned, the signal assignment operator is the less than equal to. When you use the signal assignment operator, it's what we call an implied process that will synthesize to hardware. The signal is on the left-hand side of the operator and the process is on the right-hand side. Anytime an input to the process changes on the right, that process turns on, executes the statement on the right, and assigns a new value to the signal on the left. To generate logic, we use VHDL operators. The operators can be arranged in logical, relational, arithmetic, and then some miscellaneous operators. For logical, we have not, and, or, nan, nor, XOR, and XNOR. As a note, XNOR is supported in VHDL 93 only. For relational, we have equal, not equal, less than equal to, greater than, and greater than equal to. For arithmetic, we have plus and minus for addition and subtraction. Those same two symbols can be used to indicate the sign. Multiplication indicated by the star, division by the slash. You can also do the modulus and the remainder. And then for miscellaneous operators, the double stars represents exponentiation, ABS represents absolute value, and then the ampersand represents concatenation. Thus, I can take two 4-bit vectors and concatenate them together to create a single 8-bit vector. In this example, I want to illustrate a signal being used as an interconnect. I have the entity called simp. It has two inputs, I1 and I2, which are both single bits, and a single bit output O. In the architecture, I want to AND I1 and AND I2 together, invert that, and drive it to O. Now for some reason I want this intermediate signal available, and since it's not an I/O, I then need to declare it as a signal inside of the architecture declaration section. So I declare it int as a type bit signal. Then down in the architecture section, I can assign the AND I1 and I2 together and assign them to int, and then take the result int, invert that with the not operator, and assign that to 0. So again, I and 0, I1, I2, and O are all signals by default since they're I/O, and int is a buried signal, and thus it needs to be declared inside of the architecture declaration section. In the VHDL built-in libraries, certain operators can only be used with certain data types. For example, arithmetic operators can only be used with data type integer, and Boolean operators can only be used with type bit. But what about other data types like standard logic? Well, to do this, we have to use operator overloading. Operator overloading allows the same operator to be used with multiple data types. This is done by declaring a function whose name is the same name as the operator itself. To do this, we enclose the character representing that operator in double quotes. Now to make this easier, IEEE defined data types have already been overloaded for us to use, using the same operators as the standard data types in VHDL. If we were to go into the packages that define overloaded functions in the IEEE library, such as standard logic arith, standard logic signed, standard logic unsigned, and others like numeric standard, we'd find these overloaded operators. At the bottom of this slide, you can see the example of some of the functions that are defined in the standard logic unsigned package. Thus you can see the plus sign, again notice it's in double quotes, has been overloaded so that it can accept a standard logic vector, an integer, or a standard logic vector, another standard logic vector, a standard logic vector, and a single bit standard logic, and return the result of an addition operation in the form of a standard logic vector. The same thing is shown here with the minus sign. So to use operator overloading, you do have to indicate the package that contains the operator you want to use. So in this example here, you can see that the IEEE library has been declared and the 1164 package has been specified. We also have to specify the standard logic unsigned package as it contains the unsigned operations for standard logic. Down in the code, we have two 5-bit standard logic inputs and a 5-bit standard logic output. Then down in the actual architecture body, I can say sum gets the value of A plus B. Since the plus symbol, as we saw in the last line, has been overloaded to accept a standard logic vector value on the left and the standard logic vector value on the right and produce a standard logic vector value result, this is completely valid. Now let's look at concurrent signal assignments. We use concurrent signal assignments to take expressions and assign the results of expressions to signals. When you do concurrent signal assignments, it automatically implies a process. All implied processes, all processes in general in an architecture execute in parallel. What that means is that when any signal value on the right hand side of the operator changes, that process turns on, executes, and then assigns a new value to the signal on the left. And if you have multiple signal assignments in your architecture body, then all of those signal assignments are operating in parallel and must be treated as so by both your synthesis tool and your simulation tool. There are 3 types of concurrent signal assignments: the simple signal assignment, the conditional signal assignment, and the selected signal assignment. The simple signal assignment uses the format a single signal name, the signal assignment operator, which we say gets the value of some expression on the right. So here's a couple of examples. QA gets the value of R or T. The second one, QB, gets the value of QA and not G, X, or H. Both of these 2 lines are implied processes, means that they are executing concurrently. So the order of these 2 lines does not matter. If any of the signals on the right hand side is to change, then that process, that line, turns on, executes its expression, and applies its result to the left hand side. So for example, if R changes, then the top implied process turns on, the top signal assignment turns on, executes R or T, and assigns a value to QA. If QA then changes, then the second statement turns on, executes its expression, and then assigns a new value to QB. To help with providing an order to the expression, you can use parentheses, as you can do in many languages. And just to illustrate it again, the order of these 2 lines does not matter. So if I flip them around, I would still get the exact same behavior. Signal assignments run concurrently.